This example will illustrate the methodology required to test the claim about a population mean when the population standard deviation is not known. So in this example, a hydraulics pressure sensor company claims that when their sensors are exposed to a standard fluid pressure of 125 kilopascals, that their average sensor will in fact give that reading. And so a sample of 6 randomly chosen sensors gave the following measurements: 132, 129, 124, 130, 133, and 129 kilopascals. And so we are supposed to test this manufacturer's claim to a 2% level of significance. Remember that when you do hypothesis testing, there is a standard set of rules, set of procedures that you're supposed to follow. The first is that the standard pressure of 125 kilopascals, the claim is that their sensors will in fact give that reading. So the claim that's being made about the average sensor value is that the mean will be equal to 125 kilopascals. We need to, step 2, determine whether this is the null or the alternative hypothesis. The original claim does contain an equality. Therefore, that becomes the null hypothesis. And so this is what we're going to test, whether the mean is equal to 125 kilopascals. That is the original claim. The alternative hypothesis, which is what is true should the null hypothesis be false, the only possibility is that it is not equal to 125 kilopascals for the measured average. So when you sketch this claim, the population mean is claimed to be 125 kilopascals. But if we find a sample result that gives us an average that is too high or too low, either situation would allow us to reject this claim. So you only sketch the null hypothesis, you only test the null hypothesis. Since alpha here was given a 2% level of significance, we've got alpha here of 0.02. That means because this is a two-tail test, there is 1% in each tail. This is the alpha is the likelihood that if you repeated a sample of 6 sensors, that they would give you a value that disagrees with this number by chance. And so we've got 1% on the low side, 1% on the high side, because the claim was made that it was equal to, it didn't say that it was greater than or less than, it said it was equal to 125 kilopascals. So in this particular case, because we have a sample of 6, notice there is no information given here about the population standard deviation. And so the standard deviation is going to be unknown. If the standard deviation of the population is unknown and we want to test a claim about the population mean, we are required to use Tscore. And we'll have to find both the mean of the sample and the standard deviation of the sample in order to use this test statistic. So we've got a 1% tail on the left, a 1% tail on the right. We have to use Tscore. Tscore uses degrees of freedom, which is sample size minus 1. So we've got 6 minus 1. Number of degrees of freedom here are 5. So if I look on the Tscore table, on the Tscore table, we are looking for a 2% in two tails or 1% in one tail. So that's the fourth column here. But we've got 5 degrees of freedom. So the critical T-score value should be 3.365. But because we're on either side of the distribution, either of those values being in excess of positive 3.365 or less than negative 3.365, if we find our sample lies outside of this range of T-score, it will allow us to reject the null hypothesis. So we are going to need to calculate the T-score for our sample. To calculate the T-score for our sample, we need to know the sample standard deviation and the sample mean. The two numbers that are relevant for this calculation on our sample are the sum of the values, which is 132 plus 129 plus all the way along until we hit, again, 129. So add up the 6 numbers. If you add up those 6 numbers, we end up with a value of 777. We're also going to need the sum of the squares of these values. So that means 132 squared plus 129 squared plus 124 squared until you hit, again, 129 squared. Add up the squares of all those given values, and that will give us 100,671. We can take these two values and put them into the formula for mean of a sample, sum of the values over the sample size. So that's 777 over 6. We're going to find the mean of this sample is 129.5 kilopascals. So the mean of the sample, 129.5 kilopascals, is definitely more than 125, but is it significantly more? Is it enough to lie in this rejectable or critical region for the hypothesis test? We need the standard deviation of the sample, and using the formula n sum of the squares minus sum of the values all squared over n minus 1, that gives us 6 sample size times 100,671 minus 777 squared, all divided by 6 times 5. We end up with a standard deviation here of square root of 9.9, which ends up being 3.1464 kilopascals. And so rounded, it would be 3.1 kilopascals. Both the mean and the standard deviation round to one more decimal than the data. But when we do our calculation for the T-score for the sample, is sample mean minus claimed mean over standard deviation of sample over root of sample size. This gives us 129.5 minus 125 over 3.1464 divided by root 6. And so for the sample, we get a test T-score statistic, 129.5 minus 125, all divided by our sample standard deviation, 3.1464, and divided by root 6 is times root 6. We're going to end up with a T-score calculation of 3.503. So the sample standard deviation, when we put that in, we find that it gives us a sample test statistic of 3.503. And if this is the critical score, 3.365, we can see that our sample is to the right of that. So the sample is in the rejectable region. The sample is in the critical region that allows rejection of the null hypothesis. And so, therefore, this sample lies in the critical region. Because it lies in the critical region, we have to reject the null hypothesis. And if we reject the null hypothesis, then our conclusion has to be this. Because the original claim is the null hypothesis, there is sufficient evidence to reject the claim that the average value equals 125 kilopascals. So there's sufficient evidence to reject that claim to a 0.02 significance level. So in summary, because the critical t-value of 3.365 was exceeded by the test statistic 3.503, it is just into that rejectable region. Reject the null hypothesis. Since the original claim was the null hypothesis, then our conclusion should be there is sufficient evidence to reject the claim that the measured average is 125 kilopascals to a 2% level of significance.